The final speaker of this session is Engels, so without further ado.
Yeah, thank you very much. It's a great pleasure for me to be here today and to take some of our slides with you. So just as a warning, this is an experimental talk, so I'm an experimentalist. But the idea is to give you a feeling for how we can actually manipulate the Bose-Einstein condensates and how they relate to a lot of the topics that we have heard about here in this conference. So the experiments that we are doing, they are conducted at Washington State University in close collaboration with Sean and Maren Mossman, who are former faculty members and who are now at the University of San Diego. So while we got the experiments to life in the lab, what really gives meaning to our experiments is actually all the input and expertise that we get from our friends in the theory. And so I'm very happy to acknowledge that a lot of theorists, many of them are actually at this conference over here. So we've got a very nice collaboration going on with Panos, who is online, I think, and Gino, who is here. And we study all things soliton with them and also modulation and stability. And we have got a very fruitful collaboration going on also with Mark Hofer and Boas, who was here until yesterday, and of course Patrick and Shashwat. And Shashwat also showed that poster on Monday. And with those folks, we do a lot of rarefaction-based studies. And then I would also like to acknowledge local theorists from WSU, in particular Michael Forbes and Kings at One, and Dirk Bloomer, who is now at the University of Oklahoma. So here's a brief outline of my talk. So the idea is that I want to give you a brief introduction to the disease from an experimentalist perspective, so that you see what the wave functions that you deal with actually need for an experimentalist. And then I want to show you a sequence of 3 little experiments. It's a sequence where first we're going to start with a non-interacting system, and we're going to see interesting stuff over there. On there, you know, how can something that's non-interacting and therefore non-linear really be interesting, but there's some interesting stuff in there. Then I will show you how we can manipulate and play some tricks with the interactions in the system to generate individual structures or features of interest. As a particular example, I take the Peregrine soliton, since we have heard a lot about this in this conference already. And finally, we are going to take a look at some more global dynamics in the system. And the story is here to show you how we can actually create something that's like binary turbulence and then let it recover into something that looks like a soliton gas. This is fairly new results, so this is why I'm hedging my words a little bit here, because we're still working in full analysis. So starting with the brief introduction. The basic idea is that at room temperature, you think about atoms as just billiard balls that just bounce around. But then if you cool down the atoms, quantum mechanics tells you that you should really describe your system as your atoms as wave packets. So each individual atom then is going to be a little wave packet. And the cooler you get, the larger the wavelength of this wave packet is going to be. It's an inverse relation with the momentum of the atoms. And so if you're really cold and dense enough, then you may come into a regime where the individual wave packets of the atom starts overlapping. Then they really start feeling each other, and quantum statistics come into play. And for a certain class of atoms, which are bosons, what can happen then is that all these atoms fall into one macroscopic matter wave, depicted down here. This is the Bose-Einstein condensate. And the closer you go to T equals 0, the more atoms are actually occupying this Bose-Einstein condensate. Of course, we can never reach T equals 0 exactly, but we can get pretty close. So in our experiments, we reach temperatures of about like 100 nanokelvins. So this is really, really close to absolute 0. And then we get systems where we can have maybe up to 1 million atoms or so occupying one big matter wave. These objects are then macroscopic quantum objects. We can stretch them out to a dimension of maybe up to 1 millimeter. So it's quantum physics, which normally you think describes atomic scale physics, but transported into the macroscopic world. And with this, we can then do our experiments. So this wave function that I talked about, what does it actually mean? So a single quantum mechanical particle, like the motion of an atom, is described by the Schrödinger equation. And the Schrödinger equation gives you a wave function psi. And the meaning of the wave function is such that the amplitude squared of this wave function gives the probability to find the particle somewhere. So in this picture up there, this could be the wave function for one specific particle. and I don't know where it is, I can only say with a certain probability where I'm going to find it. So if I take one photo, I get one click afterwards, like this click indicated over there, at a position that's given somewhere by the amplitude squared of this wave function. Now in the Bose-Einstein condensates, we actually have got 1 million atoms in there. 1 million atoms in the same wave function. So if I then take a photo of this thing, I get 1 million clicks. So what this gives me is the wave function squared in one image. So in a single image, I can actually map wave function squared of my wave functions. So the equation that we use is the nonlinear Schrödinger equation. And in our field, it's often called the Gross-Pitayevsky equation. You can derive it from many different angles. For physicists, this is the very natural equation. In quantum mechanics, the momentum of the particle is given by h bar over m times h bar over I times the radiant. So the first term over here is then p squared over 2m, which is kinetic energy. Then, of course, I've got potential energy over here. And then I want to take into account that all the atoms are interacting with each other. And the interaction energy is higher in regimes where the density is higher, because you've got more particles interacting. And so you end up with a term over here where psi squared is the local density. And you can think of it effectively as another potential term. And what's nice is that all these terms are experimentally under control. We can play tricks to change the dispersion using, for example, additional laser beams and Raman coupling and what have you. You can make potentials that are either static or moving or in special shapes, localized, large potentials, whatever you want. And within limits, you can also adjust the interactions in the system using tricks like Feshbach resonances that play out for certain elements, not for every element. In addition to this, you can also have multiple copies of the quantum state, because atoms have got internal states. So there's a whole range of different internal states, and each one would be described by one of these nonlinear Schrödinger equations. And we can couple all the different states of RF and microwave radiation. So in the lab, typically this is realized in machines which look like this. This is the heart of the machine. What you see in the very center over here is a little cuvette, a little glass cell that's hooked up to ultra-high vacuum pumps. The size of this glass cell is about 1 inch, 2.54 centimeters. And what you see around here, like all the copper stuff, that's just magnets that we use to confine the cloud in the middle of the ultra-high vacuum chamber. Then this is immersed in a large mass of lasers that we use for laser cooling and to prepare and imaging the system. So the thing that you saw before is just at the very center over here. This is where the VEC is created, and everything around it is just for laser cooling, for creating the potentials, and for doing the imaging in the end. So the imaging is really done with just the CCD camera over here, but our images are very fast, like 10 microsecond exposure time. Using lasers to lasers that are absorbed by the cloud, and then we image the shadow on the VEC. Now, these systems provide quite a new and a unique tool with which the study of superflow can actually be pushed into new regimes. So compared to the liquid helium system, superfluid helium, which you had before, these systems are actually dilute gases. And that means that the density is lower, so the healing length is larger. The healing length means how quickly or how slowly can a wave function rise from 0 to about value, which means that all the features are much larger. So vortices and solitons, they are on a much larger scale, and you can directly image them. And so there have been a lot of experiments with hydrodynamics, in particular in these systems. This is, for example, a rotating Bose-Einstein condensate. It was spinning about by about 8 hertz in this direction. And what you see there is all the Swiss cheese-like structure. So this is false color imaging, false color coding of the density. So that means lots of density, black means low density. So what you have here is very nice abricosa lattice of vortices. Then you can actually deform this, excite surface phase, melt your surface, your vortex lattice over here. You can play with vortex, anti-vortex pairs over here. There's a lot of work that we and others did in dispersive shock waves. This is where we benefited a lot from Mark Höfer in this group. With Mark together, we've also done a quantum realization of a piston shock experiment. And this also has interesting relations to optics, because the Panatrios group has done something similar in optics. There's all kinds of turbulence in these systems. There's vortex turbulence, there's wave turbulence, there's spin turbulence. All kinds of solitons have been realized. You can do counterflow between two components and get modulation of instability, or you can generate caustics, for example, which I will talk about next a little bit. So there are a lot of omissions over here and a lot of spectacular results. So let me come to the first example that I wanted to present, which is a non-interacting system, and you may wonder, why is this interesting? So, well, one of the hallmark features of quantum mechanics is that atoms behave like waves. And one of the hallmark features of waves is that they can interfere. Now, if you have got interfering waves, you can do interferometry. And so this is the basis for a lot of high quantum sensors of high sensitivity. And one example is shown over here, how you can exploit matter waves actually to sense stuff. So what we had here, this is an example from my group. We had a Bose-Einstein condensate over here that's confined in a trap, and we coherently allow a small fraction of the atoms to always fall out of the trap. Then by gravity, these atoms are accelerated downwards, and you end up with a stream of atoms streaming downward, which is completely coherent. So this is the matter wave analog of a laser. So this is why it's called an atom laser. It's a coherent stream of atoms. Then we can play with the internal states. We can put the solar atomic beam into two internal states, give these states different phase evolutions, re-interfere them, and look for the patterns that we see. And then, for example, if you've got a magnetic field that manipulates the two states in different ways, you can sense magnetic fields. If you look at this picture over here, you see all these horizontal stripes. This is a measure of a magnetic field gradient that was applied along the vertical direction over here. You also see this bullseye pattern over here. This was because we had an optical potential crossing it, and we were trying to measure this optical potential using atom interferometry. So this works really nice, and using internal states for interferometry is really the basis for atomic clocks and many types of sensors. What is more tricky, surprisingly, is actually to observe interference of just one state if you've got like different flows of the condensate that just run into each other. And this is difficult from an experimental point of view, because if you've got flows running into each other, typically the relative velocity is such that it's a little too large for features to be seen directly. In other words, like the de Broglie wavelength, this relative motion would be too large. And also the dynamics are often obscured by interactions. So for example, if you've got a BEC and you just slice it in the middle over here, and then you just let these two parts actually come together and collide, you are not going to see like a trigonometric interference pattern, but you are going to see high spike and turbulence over here and dispersive shocks. You see all these little ripples spreading out, and then in the end, the whole BEC is filled with solitons. So if you want to see interference patterns, you need to be in a very dilute regime. So this is some original data from Wolfgang Kedeler. Other examples are, for example, specialized situations where people did some ring flow over here in this outer ring, and then used the center as some stationary phase reservoir. Then you let things expand into each other, and you can see these spiral patterns here as a signature of the ring that's introduced in the blowout cycle. So what we were interested in is actually to generate the matter wave interference in more general and more maybe more interesting situations than just two halves running into each other. And one prominent example is given by caustics. So how do we generate caustics? If you've got a BEC over here, this needle, and you couple out atoms, so you get this stream of atoms running down, that's an atom laser. And then if you put potentials crossing the atom's laser, like a laser beam shining by here, the atoms bounce off this potential. And if this potential is of a Gaussian shape, you can get very nice caustics. For example, you see the caustics here, or here we have another potential in there. Caustics are, of course, all over the place in optics. And there's a theory called catastrophe theory that describes different kinds of optics. There's cusps and folds and what have you. But they're also appearing in other regimes. And I would like to point out the work by our friend Duncan Hodel, for example, who studies caustics in quantum systems. So there's also very interesting work done in quantum many-body dynamics where caustics actually show up. And then you see in optics, these are pictures from optics, that these caustics are actually supposed to be decorated by fine interference fringes. So if you've got a certain caustics that's a fold, you're supposed to see like an airy type pattern. If you've got a cusp like this edge over here, you're supposed to see something that's described by a Pearcey function. And from an experimental point of view, how do you actually get the caustics? Well, from our point of view, you would have like a plane wave running downstairs, running downwards over here, and then says there's something that destroys the wavefront. So after running through some piece of glass or a drop of water or something, the wavefront looks like this over here. How does this propagate further? Well, locally, the rule is that locally your propagation direction is orthogonal to the wavefront. So this part moves down here, this part moves down here, this part moves down here, and then this part moves down here. So you will actually see how trajectories bunch up at this one point over here. This is just one snapshot in time, so this whole thing is evolving, of course. And this would be one point on the caustics, so this point over here. Now, in these experiments, unfortunately, the decorating interference fringes were too small to be seen, so we changed our setup, and instead we go to a large blob of the BEC, very thin little blob, and we just pull the potentials through the cloud, which by Galilean invariance should be kind of like similar. So here we've got the very large BEC. You see this scale is about 100 microns, so it's really macroscopic. And then we can pull barriers through this cloud, either attractive or repulsive barriers. And we can do this for different potential heights. This is a 65 nanokelvin deep potential. This is higher, and this is even higher. And you can see very nicely all these interference fringes originating from the caustics over here. So this is just a zoomed out version. And I think this is the first time that people actually are able to see beta wave interference in a non-trivial arrangement over such a large length scale. This is almost like a millimeter. And in principle, in theory, you know, in theory, in this case, these patterns here should be described by an area function. And earlier in this conference, finally, we had a comment about doing a quantum analog simulation of the area function. This could be an alternative approach to it. If you do this for a gust, then you're going to see more complicated pictures. These features over here, these diamond-like tiles, they are supposed to be described by a piercing integral hidden over there. And we've also found some experimental settings where we are now able to see piercing integrals in the experiment. So let me move on and talk about the next step, where now we want to actually add interactions to the game. And one interesting application of it was the realization of the Peregrine soliton. So it's a particular pleasure for me to speak here because we also had heard about the Peregrine soliton in the water tank in Ameenstock. And so what's the idea for the Bose-Einstein condensates? So in Bose-Einstein condensates, there's a long history of research in solitons. People soon after making a BEC started imprinting the soliton face on the BEC, and then so it actually evolved into a soliton. There are different types of solitons that were realized. Together with Mark Höfer, we worked on dark white solitons that we induced by counterflow, like having two different hyperfine states, moving them through each other, seeing dark white solitons like this atom actually sits in here during the evolution. Just for imaging, we vertically put them apart. So, solitons have also been generated by starting with a defocusing equation and then jumping to a focusing equation, or in other words, changing the interactions from attractive to repulsive. And then when the units group, for example, you saw the emergence of these individual blobs over here interpreted as the emergence of bright solitons in the system. Now, at the INI workshop in December in 2022, we actually reported on the technique where we can bind up a condensate, where we have got two different species, and we create phase bindings in them. And I'm just showing one of the two species over here. So you can see patterns of atoms over here, and the dark gaps are actually filled with the second component. And we were able to create phase jumps between all these, and this was a starting point for actually seeing soliton complexes, which are akin to what people talk about the soliton gas in other contexts. So here I want to focus on the Peregrine soliton. And I don't have to really introduce it. On the left-hand side, we've got the bright soliton, which sits in the zero background. The Peregrine soliton is a soliton that has got spatial temporal localization. So it comes and goes and then end of story. And this is also a candidate for waves. The Peregrine soliton is very distinct from the bright soliton, for example, by the occurrence of these two density dips over here, which are not there because this thing is not sitting on a zero background. So you've got a finite background and these two dips over here, and then there's this whole temporal evolution. Now, the Peregrine soliton was actually first predicted by Howard Peregrine, who was at the University of Bristol. And then it took about 25 years before the first observation came about, which is surprising because this is such a nice hallmark feature of nonlinear dynamics, something that comes and goes apparently on its own. And so there were first observations in fiber optics and also in water tank by Amin over here, who gave a very beautiful talk in this workshop already, and also in multicomponent plasmas. And in 2022, there was even a Frontiers in Physics research topic edition that commemorates the 10th anniversary of the observation of Peregrine solitons. So we also wanted to do Peregrine solitons. And we were working on this together with Carlos and with his team and Gino. And the idea is the following. You need an attractive interaction in the cloud. But if the attractive interactions are too strong, then all the dynamics are overwhelmed by just modulation and instability. So you have to be delicate. Also, this Peregrine soliton comes and goes. So you want to actually be able to make it in a deterministic way, so that you can actually follow it and see it come and go over time. So for our condensates, all the interactions are actually repulsive between the atoms. So that's a little problem. So this nonlinearity over here has got a positive sign. But what you can do is you can play with two different species. And the idea is that if you take one hyperpunct state and just a minority of atoms in here, and you immerse it in a big bath of the other hyperpunct state, this one over here, then if you focus on the minority state, you can actually see kind of like a renormalized interaction. So this interaction gets changed because it's sitting in the big bath of the first component. And this is exactly what we did over here. There's a formula over here that tells you how the interaction strength gets modified around. And the key is that for the particular components that we use, the effective interactions for the minority then become slightly attractive. So this was the first key ingredient, how we can start with a repulsive interaction, but use two components that are slightly immiscible, and then the minority component is going to want to separate out from the bath because they are immiscible. And from the perspective of the minority, it looks like as if it had attractive interactions.
So just to clarify, is it correct to say that you're considering in terms of the equation, it also is the equation two components? Potentially because of the carbon you're not in a special case. Right. So that's what makes it possible to play with the constants, the lovely constants between the different modes.
We are very close to monocouple. So you see here, we've got 94.5, 98.9, and 100.8. So if they all were the same, then all were the same.
I see.
So it's very close.
Thank you.
Mm-hmm. And this has also been used by the Balibar group to create a town soliton, which is the only stable one in 2 dimensions, right? We write soliton for the Okay, the second thing that we need is we need to actually not only prepare the system, we also need to send it on its way to form the Peregrine soliton. And we do this in the experiment by creating like a little density hump in the middle of the cloud. So we can do this just with the additional laser beam that's a little bit attractive, and we focus it on the center of the cloud and pulls the atoms in. And then this is the main result for the Peregrine. So you create a little density hump in the VEC. You then create this mixture. So you turn on the negative interactions, the immiscibility, and you can see how over time you start with the little hump. The hump steepens up, and you get this feature over here. These are integrated cross sections. And you can see the very nice dips in here. Then the dynamic goes on, and you can see how we get almost a full modulation over here. So this is indeed the Peregrine shape with the characteristic dips in there. And then the Peregrine goes away again. Then you see some remnants over here. And then at even longer times, the modulation and instability in the system kicks in. So all this is before the natural MI of the system actually starts controlling our dynamics. We can take a look at the solutions, but since most of you are experts in here, I'll just jump over it. Now, let me just say from a physicist point of view, what we would see here is we will take a look at the phase, which is plotted in red. We see phase gradients over here. Phase gradients for us means it's a current flow inwards, so the atoms are actually rushing inwards over here, and then it forms the peak over here. And since the peak is high, the phase of emission there is a little faster than outside. So at some point, you reach the point where you've got a phase jump of phase difference of pi between center and middle. That means inside and outside interfere destructively, which means you actually get a dip over here. And then pi is the same as minus pi. So the phase jump rate inverts, and now you've got opposite gradients and the matrix run out. Okay. Finally, let me just spend a few minutes on the last talk, the emergence and decay of turbulence in a two-component BEC. I put it in quotation marks because it's not really analyzed in full detail, but I think this is pretty much the storyline over here, but I'm just hedging it a little bit because this is still ongoing work. So in the workshop at the IMI in Cambridge, we presented the technique how we can actually bind up the BEC in the following sense. We can take two different hyperpoint states over here. And now these hyperpoint states that we picked are miscible. So if we just make a BEC of the two components, nothing really happens. They just happily sit on top of each other. And what we were able to do is actually to make a situation where we've got one component, second component, one component, second component. So we are going to make these slices. And we are able to actually engineer phase jumps from between like components, phase jumps of pi in there. And then the workshop in Cambridge, we used this as the starting point. We let the system evolve and we saw kind of like soliton gas-like dynamics. What I want to show here is the following now. What we've done recently is we've implemented a differential force on the atoms, such that now we can take one component and pull it to the left, and we can take the other component and simultaneously pull it to the right. So what I'm showing you here is these two components, they are just separated out for imaging. So while all the dynamics is going on, this thing really looks like over this, where they are staggered inside next to each other. But then just for imaging, we use the Standout technique to just put them apart. So I can show you the two components over here. And then in the following, just for simplicity, I will just show you one of the two components because the other one is complementary. Because we're looking at spin dynamics, which has got much less energy, much less chemical potential than the overall density dynamics. Okay, and then I'm going to show you three different runs of the experiments. These are just repetitions because each time when we image the BEC, we destroy its quantum. So we need to start over each time. So just that you can see how repeatable the experiment is, these are three independent runs of the BEC. This is just the initial condition, having this bound-up cloud over here with the phase jump of pi between each one of those, and just showing you one of the two components. Then we are going to apply the differential force. And this is a time slice, 1 millisecond, 2, 3, 4, 5, 6. The different columns are just again different repetitions. So maybe I recommend just focusing on the first one over here. And then if you want to see how repeatable it is, you can look at the other one. So what you see is that the initial winding structure actually disappears after 6 milliseconds. Here we go on 7, 8, 9, 10 milliseconds. And at 10 milliseconds, so the initial structure has disappeared. And we end up with the BEC that for us experimentalists has got an unhealthy roughness to it. So we clearly know that these BECs are unhappy. And this is because they are actually in a turbulent state. This needs to be confirmed by numerics, but we do have indications for that. For example, if I just plot like a 90% percentile, so atoms between 90 and 100% of the density, I can see in this case that I have got a lot of like holes, like these guys over here, or if I see a pair of holes, I would identify them with the vortex ring inside. You have to remember that we always image to the whole cloud, so this is not just a slice. So we clearly see that the BEC in our turbulent state is unhappy. There's a lot of stuff going on. For comparison, the upper one is just BEC where we made the same density and we didn't do anything to it. It's just happily sitting around. So what we have shown you here is how we can presumably drive the BEC into a state of binary turbulence. And then the question is, well, you can also turn the drive off and then see what the system does afterwards. So this is shown over here. Now we start with this presumably turbulent state, and we turn the differential force off. And what you see is that the state actually persists for a certain while. This is like 6 milliseconds down here. Goes on and on and on. 20 milliseconds. Oh, and then we start, there's some interesting dynamics happening because you're going to see all these spiky features occur in the BEC. And note that they all have a very, very consistent width to them. And by having played with PECs in different types of experiments, we know that these are actually solitonic sizes. So these are solitonic excitations that we see in the PEC. So you see after this turbulent state, the system actually rearranges itself into a nice soliton gas-like feature, calling it a soliton gas just from the phenomenological image that I'm showing you over here. You can see each repetition is slightly different. And then this state qualitatively stays the same for a long time. So this is the picture at 40 milliseconds. If I would show you the picture at 80 milliseconds, you wouldn't be able to say which one came first, because the dynamics is qualitatively the same. And here we went out to 100 milliseconds. So what we see is that from this turbulent state, we actually see that solitons emerge. This may actually relate to a general comment that we had earlier in this workshop, saying that if you've got a system with strong nonlinear dynamics, it's prone to actually forming the solitons. And the soliton state is actually fairly persistent. And so what we want to claim here is that the solitons might act as a mechanism to absorb the energy from the turbulent state. And the solitons therefore generate an effective viscosity maybe in the system that actually takes energy out of turbulence, like a damping mechanism in there. But this is with a question mark because we still have to run the dynamics. I just want to point out that the soliton sizes that we see at the end is very different from the binding size. This binding size is something that we engineer into the system. I can make wide or small events, whatever you want, and I happen to make these ones over here. This is the size that the system actually chooses on its own, because it's the typical soliton size in this image. What's the relevance of this? So, and this is going to be my last slide. So in the field of closed quantum systems, there's a lot of discussion about thermalization of the system. If you've got a quantum system and you take it out of equilibrium, how does the quantum system actually thermalize it? And one example is shown. So typically would expect maybe if you take a system out of equilibrium and maybe smoothly and then maybe the square root of t function or whatever relaxes back to equilibrium. There's like an ETH, like an eigenstate thermalization hypothesis or whatever. But in reality, things can be much more complicated. So this is, for example, a numerical study of a superfluid Fermi gas. It's not a BEC, it's a superfluid Fermi gas. People have seen a little bit more depth in the system. This was done by our collaborators, friend Oren Bulgak from the University of Washington. This is a simulation where he studied the superfluid Fermi gas and initiated it in a box with 12 vortex antibodies. So overall, there was a lot of current in there, but no net vorticity. Like vortex and anti-vortices indeed. This is a numerical simulation that was run on the Frontier and Summit supercomputers at Oak Ridge National Lab. And so what they see is that after a while, of course, these vortices start bending, and then you see your vortex rings, vortex recollections, which by Feynman would be, turbulence in the quantum system. And then, interestingly, things just don't go on and dissipate into phonons, but there's a phase again that emerges over here. This is time. There's a phase where you end up with 4 vortices back in the system. And they stick around for a while. And then after some time, they annihilate into vortex rings. And then you actually see you've got these density ripples like over here. So there's different stages in the damping of the turbulence. It's not just that a non-equilibrium quantum system will directly go back on a smooth way into an equilibrium. It can be very different. Maybe one may conjecture that what we see when we recover from the turbulent state and we see the emergence of the soliton structures, maybe this is also related to something which is seen here, where you've got this vortex mess, and then you've got the emergence of vortex, a smaller vortex system over here.
In the new model, you are kind of near to it.
Yeah, but in real life, interconductivity is always broken by a lot of things. To show the harmonic trap-on, there's all these interactions. But
yes, here the vortices are very well separated. Imagine that in your solitons, they seem to be like that.
Yeah.
Kind of thing here.
Yeah, and this is done using this is time-dependent density function here, TDS and the changes. So it's very computationally expensive already. Okay, yeah, thank you. I'm sorry for being a few minutes over, but
not straightforward. Most many colleagues have asked about various sorts of PECs. Definitely great results. So I would be interested to know what would be the experimental challenges to generate a second order Ohio Peregrine.
Very good question. So the question is, how do we actually, could we go about to go to higher order Peregrines? Probably getting the initial conditions right, so that the system actually wants to evolve into the higher order Peregrine. You know, probably you need some very nice, precise way of shaping the initial dynamics so that it would actually form it.
There's no physical limits for higher order Peregrine, say, have an implication of 2n plus 1. So is there like a limit order, let's say, observation?
I think from my point of view, anything above the ground one is tricky, you know. The higher order ones will also have higher peaks, so they should be nice to discern, but I think getting the initial conditions right is a problem. Now, there are some ways how you can make almost arbitrary initial conditions by leveraging digital micromirror devices. So in our case, we just have a Gaussian beam that creates a little hump. In principle, you can shape this to any kind of shape that you like, but then you will run into optical resolution limits, like how narrow can you make the initial hump. Fortunately, the soliton, the Peregrine soliton, the ground state was very forgiving to whatever we did. Like Alejandro from University of Vermont, he did numerical studies where he tried wide and narrow ones, and they all ended up in the Peregrine soliton. What's even more, you don't have to leave the barrier on initially. You can also just make an initial barrier and then turn the initial potential off that creates this hump, and the system is still going to develop into a Peregrine. So once you have the system set up, actually the experimental parameter don't have to be fine-tuned so well. It just depends on, how much time the Peregrine emerges. It doesn't turn out after 40 milliseconds or after 80 milliseconds. But in the experiments, we can just spend. And the nice thing is with this feature, you can produce it reliably and repeatedly and deterministically. So even though it's kind of like an instability, since we initiate the system, we have got a very consistent time sequence. So all the images that I showed there are from different repetitions of the experiment. So each time you make a BC, take the image, make a BC, take the image, make a BC, take the image. So on a good day, we can maybe average like 1,000 ones or something.
I think we were on the front row. That's
Okay, thank you very much. I'm ignorant. What you had a Peregrine soliton, you had a soliton. Can you say in simple terms what is the nonlinearity in this evolution, and what is, in simple terms, what is a dispersion? Now you point out.
The nonlinearity comes from the interactions of between the atoms. So if you look at the Dostoevsky equation over here, so the first two terms would just be kinetic energy leading to some dispersion. So if you only would have this, in a Gaussian hump, it would just disperse away. So you put like a p squared over 2m over here. This is just the potential. Over here, we mimic, from an experimental point of view, the interactions of the system by having a potential in there that is higher where the atoms are denser. So more density means the interaction energy in this area of the BC is higher. Now the local density is described by wave function psi squared. And so I've got here a term that's psi squared times psi, and so this gives me a cubic nonlinearity in the system. We also have a very nice poster at this workshop where someone studied, peregrines in higher order nonlinearities of fourth order, and what you see there is then that you also have got shedding of energy out of the peregrines. But over here we have the cubic. So all the nonlinearities in the system, and those are really at the heart of solitons and vortices and what have you. It's really because of the interactions of the system.
Thank you.
Yeah, so I guess I'm a little surprised that you see Peregrine and not like who's going to model these periodic things, just because they're, in terms of the solid and eigenvalues, it's more typical. Do you have any comment about that? Why it means?
Well, there's of Brown, there's also aggregate breeders and all this.
Yeah, you're like when you excite it, right? The sense of localized.
Mhm.
It's
Gio, do you have a comment on?
Well, I think it's because it's the virtual scenario. If you have focusing instability generically at the peak, you're gonna get, then you see part of it. Sorry? Then you should see a lot of them. Sometimes you do, sometimes in the simulations, Alejandro saw, a bunch of them afterwards, but experimentally, it gets harder because you need to be able to control the signal all the time.
Yeah, and then also, once the Peregrine actually decays again, if things are a little bit asymmetric, things can get shifted a little bit to the side, and then soon thereafter, after maybe 200 milliseconds, the natural modulation instability of the system kicks in. And so then you get roughness in the system on its own because of the amount.
And actually, two questions, but maybe I would just ask not like how much is involved in the three nature of the like, are you tracking with the nature or any corrections for the max?
This is a very good question that always shows up for a lot of our experiments, not only the Peregrine, but also the dispersive shock waves and so on. And then the answer is always, what do you mean by being 1D? There are different degrees for us experimentalists of 1D-ness. And so, for example, if I excite a sound wave in the DEC, and I've got an integrated DEC, if I see a sound wave that's just not bending or anything, but smoothly running through the DEC, just on that, I would call this effectively 1D. But it may be that my chemical potential is so high that I have several radiant modes still occupied. In our system, we have got about 7 radiant modes occupied in the system, but the dynamics that we see is predominantly 1D, which means that excitations in the radiant modes don't really come into play.
From the perspective, wouldn't also the flexibility like pieces. So you like one dimensional system, many pieces, one for each.
I suppose so, but then we would also have coupling between others, right? But just to, so we have got 1D numerics, then we also have got full 3D-dimensional numerics, like CMOS, Mr. and Lear, they made 3D-dimensional numerics. We compared them to the 1D-dimensional numerics. There were differences between them. So like concerning the height and maybe the onset time or something of the Peregrine, but the overall picture is exact. But we definitely correct, there are corrections to the because of the 3D-ness of the system. But earlier we also had experiments about the linear model, for example, and there was results shown from Isabelle Bouchou, and those are really more in the 1D regime where you want to suppress the chemical potential into just the lowest radiant mode. So there are different degrees of 1D-ness and already the conventions.
Yes, please.
So I'm wondering, why they was just one side, and why they were not solitons of different sides, and 45
Yeah, so in a soliton in these systems, you've got a balance between dispersion and interactions, right? So if I've got with the dark soliton, I would just have a notch in the condensate, and I would say I've got the fluid rushing inwards. That's given by the need-free interaction. I actually want to close the gap, but if the gap closes, then I get more curvature in the bottom. And so at the bottom, I pick up more kinetic energy because curvature is kinetic energy, and all this balances out to a certain length scale. And then you can say roughly this is given by the healing length of the system. Imagine you've got a DEC and you put a hard wall in there, which forces the density to be 0 over there. You can't go immediately from 0 to the bulk density because that would require an infinite curvature of the wave function. And the P squared over 2m, like the first term and the last term, is kinetic energy of the system. So therefore, there's a characteristic length scale over which the wave function actually recovers from the 0 that you force in there through the bulk wave. This is again like this healing. So the healing length shows up in many of these features. And also in the core of vortices, for example, it's related to the healing. And this, in our case, we're lucky that we have got dark bright solitons. So What appears as just a dark knot is actually built on the second component. So then we talk about spin heating lengths and all these things, but eventually this is where it comes from. It's the computation of the curvature energy and the interaction.
But when you consider just the less, yeah, then solitons is one round yes, they depend on the spectrum parameter. So why do we not see something like that here? Why is it one side?
You know, we have an answer for that.
I'm sorry, I missed the Peregrine's last name.
Why is it solitons with different sides? Why is it just one
I
side?
think it's really that's just my impression. Yeah, I don't know if I'm right, but I think it's related to what Peter said, that these are essentially dark light structures, and because they're dark light, there's a fixed amplitude that's the background, and that I think determines also their light.
So it's basically not
That's
six
my.
solitons.
But in principle, you still have
In
one
principle, you
parameter.
could still-
So it must have to do with the.
I don't know. It's a good question.
Condensates.
Yeah.
How big is H bar squared of the two atoms experiments?
I wouldn't be able to give you a number right off the top of my head, but typically it's tiny compared to the potential images. So it's very, very tiny. We want to plug in numbers. So I can tell, we usually think about healing. It's something like this initiative, the EC actually goes from 0 to 5, right? This is less than a micron.
I think that would be square.
It also has with the density. One of us sort of big pi of density and we experiment with this. It would be more usual number for us to.
Great. I'm conscious it's lunchtime, so let's thank Peter and all of the other people.